Structures. Before we begin that, is there any questions about your assignment that is up and that you should be doing? There are tons of questions this morning, and given that there's a lot of questions asked to me in my office hour, it gives me the impression that many people don't understand what's happening. Right, so do you have any clarifying questions you want to ask? Okay, have you read the assignment statement at least? You have to at least read the assignment statement. You don't have to commit to doing anything, but you should at least load it into your brain so you can think about it. You're going to have to create an intermediate data structure. You're going to have to work with a tree. So hopefully that's going to be okay. Okay, well, if there's no questions regarding clarification on the assignment, which I find strange, we'll just move on to the lecture then. So I think this is the example we ended on last week, where I asked, what is the size of this struct? Does anyone want to tell me what the size of this struct is? I heard the correct answer. 24, yeah? 20 character bytes and 1 integer, which is 4 bytes. So we have 24 bytes. So the size of this structure is 24 bytes. Of course, we can dynamically or statically allocate this, which is why we have this funny arrow references. So let's see how much of this we can actually do. Here's a good question. Suppose I create, well, I'm just using this student structure, and let's walk through the following code. So I'm going to create a structure. I'm going to create an array of students on the stack. And the first student is going to be named Alice with student number 1, 2, 3. The second student is named Bob with student number 2, 3, 4. Now I'm going to declare a pointer to student. I'm going to point it at the beginning of the array and add 1. So let's stop here. At line 10, where does S1 point to? Huh? Well, it's pointing to student Bob, essentially. So the pointer is right at B. All right? So then I take that pointer that's pointing right at B in memory, and I tell it to forget its typing information. So I'm just going to tell it that it's a void pointer now, which is the same thing as a character pointer. So P is the voided pointer of S1. So what happens when I go 20 cells along P? So given that we have a midterm, like not this Friday, but the one following, we're all going to have to start answering these questions a little bit more confidently, right? Because you're going to have to answer them on paper. Right? So let's not leave this for later. Let's try to do this now. Okay, so we have a pointer that points at B, right? So we have a space in memory which is allocated how many bytes of memory for a name? 20. So what is the effect of this? Okay, so when we added 1 here, the computer knew to walk by 24 bytes, right? That's why we're pointing at Bob, right? The reason that it knows to walk by 24 bytes is because this pointer is typed, right? And it knows that it has to walk by 24 bytes to get to the next cell in the array. This basically says, remove your typing information. So now this plus 20 actually means walk 20 bytes down memory, right? Because that's the length of a void pointer, which is the same as a character pointer, right? You're just moving by 1. So this arithmetic is now saying, starting at B, walk 20 bytes down memory. If you walk 20 bytes down memory from B, what do you find? Nope. If I'm pointing at B and I walk to 20, I'm now at the first byte of the student number. If I then cast that as an integer pointer, it's going to go ahead and interpret the following 4 bytes as an integer and print it. So if I print, what should it print? 2, 3, 4. So I'm just going to show you that that is the case. I have to contort. Where did it go here? And I think we have this guy. Yes, okay, so this is just the thing that I showed you. And I'm just going to run it. 2, 3, 4. Okay? You need to be very comfortable with questions like this. I wouldn't even qualify this as a difficult question. Right? Because if you have the memory model in your mind, yes.
Why is there a star on the other side of the
Here? Because we have to dereference to P. Because we're printing an integer. So this is basically saying, okay, because P is a void pointer. So if I told it to print, it only, if I dereferenced the void pointer, it only interprets 1 byte as the piece of information we want to look at. By telling it, no, recast yourself as an integer pointer, you should look at the next 4 bytes of what you've pointed at. And then dereference, right? So give me the value, and give me those 4 bytes interpreted as an integer value. So that's why we have to do that. Cool. But this is a perfect question, right? Because this basically combines all of the new concepts that you've learned, right? Referencing, dereferencing, and the memory model. But you really, really do need a good understanding of the memory model to be successful on your midterm, right? So if stuff like this is still a little bit difficult for you, come see me, or you have to go back and redo those PCRSs, right? Because there's no avoiding it. You're going to be tested on this. And moving forward on in your careers, this is going to become more and more relevant. Okay, so now let's do some coding. So we're going to define a max name size. Remember, this is a technique that we use to try to protect ourselves from buffer overflow errors, simply by putting a hard limit onto the to the length of strings, in this case, in the player stack. So what they want us to do is declare a struct. Okay, so here's a player struct. It has a name, a position, the number of home runs, and the batting average. So no one from my last class, what's a batting average? Anyone? See, sports analogy, sports are terrible for computer science. Yeah. Oh, I was totally off then. So I assume the batting average was like the proportion of balls you hit that were thrown at you. So is that close to it? Whatever the case, these are values that are meaningful for people who understand baseball. Yeah.
I'm pretty sure it's the amount you hit and actually get on base or further.
None of those words mean anything to me. So I've never been on base, right? And for a variety of reasons. Okay. So we have this struct player. We're going to fill it with baseball meaningful information. So notice we've done 2 things here, right? So who is the one declaring the space for the name? I guess that's a sort of ambiguous question. When I say, so when you're programming, that's you, and everyone else using your program is the user. Right, so I've given you two names, you and user. So who is responsible for allocating memory for the name for player? I guess that would be us, the programmer. Right? Who is responsible for allocating memory for the position string? The caller, right? So I'm saying here, I have a structure. If you ask me to allocate some space for this structure, I am allocating space for 20 characters, 1 integer, 1 float, and a pointer to a string, right? So position and name are a little bit different. Name, I'm handling the memory allocation for name. Someone else is handling the memory allocation for position, right? Because when you instantiate this structure, position just saying point me to the string. I don't want to actually hold you in my structure. So again, what is the space necessary to malloc player in this one would be 32 character bytes, 1 address, 1 integer, and 1 float. Right? So it's meaningful that those 2 strings have been declared a little bit differently. We're definitely going to be testing you on these string nuances on your midterm. Okay, so let's get this into a listing. And of course, I did this. I have to go back in. And which one did I call it? Sandbox? Is this it? Yeah, okay. Just going to open my sandbox, and I'm just going to delete everything, because those are the answers from last class. Blah. Okay. So I think this looks like this. Perfect. Let's just print something just to make sure that we're all on the same page. Let's just go ahead and run this. Perfect. Okay, declare a struct player on P1 on the stack. Initialize P1 to represent the third baseman, John Donaldson. whose batting average is .297. He has hit 41 home runs. Okay, how do I declare a struct on the stack? Yes, sir. Okay, so that allocates how much on the local stack frame. Okay, so let's now put the information. So we have indeed allocated memory for this playa on the main stack frame. Now we have to fill it, and we have to be careful with how we fill it because we don't want to start filling up other parts of memory in order to fill up stack memory. Okay, so I'm going to do the easy one. So playa. Now how do I set its home runs? Yes, sir. This way? No. Dot. Okay, so this is the other thing we're going to talk about. So this is notation. This is unrequired, right? We already had the necessary mechanisms for dealing with pointers to strings. Right, so let's forget about pointing to structures for the time being. But we need those arrows for when these pointers are pointers rather than structures. So this is easy. This is just a real honest-to-God variable that's a structure. So I can say playa dot home runs gets runes 1. He had 1 home run. My playa is average. Oh, I'm supposed to be putting this stuff in. 41, 2.97. Okay, and let's just give these a print. So 2, 3, 4, and what do I want? I want home runs as an integer. So I say home runs. Nope, playa dot home runs. This is a float. So it should be playa dot average. All right, so let's get rid of these. Now let's see that this has worked. Whoops. Oh, right. We don't need this. Okay, so 41 and .297 has been loaded, and those definitely live in the stack. How do I now get the names into this structure so that they're on the stack as well? Oh boy. This is concerning. Okay, so let's try to figure out as much as we can then, right? So given that we have no idea where to start, now we just have to start eliminating, right? We definitely shouldn't put it in the global memory space, right? We shouldn't create a string literal. That's overdoing it, right? I've lost my opportunity. Well, I've lost my opportunity to use the fast. Do you know how you can say something like, I can always declare a character array like this? That's on the stack, right? That's in the global memory space. Okay, so I can always do this, right? Create Paul on the stack, but then I just have to copy that into the structure, right? So I've just created a duplicate of Paul, which is not the greatest idea. Okay, but what I do need to do this for for position, right? So I'm going to say this is the position of the player, and let's say third baseman. Okay, now I can say playa dot position is this. Okay, position. And position definitely lives on the stack, right? So let me just get that out too.
Position currently set as a pointer to a pointer.
Whoops, yes, that's redundant. Player dot position. Okay, so this should work as well. Okay, so this is in the stack. This is pointing to in the stack, so everything's still on the stack. So now how do I get the name onto the stack? Okay, string copy is a answer. Okay, so let's do that one first. So I can say something like, give me a character pointer to a name and let that name be this Josh Donaldson. And then I can say something like string copy into playa.name, this name. Is there anything else I have to give it, or is that it? I think that's it. And that should work. At the end? I was going to try this for, hold on. No, it worked. I think null you have to use for, I think you're thinking of string to long.
No, I mean, you add a null character at the end.
Oh, yeah, maybe. Well, this one automatically has a null character put there. This one does not have a null, automatically put a null character there. So maybe I should actually put it there. Okay, but what have we done here? So technically, we have a structure player on the main stack frame. But here's what I say. You put this Josh Donaldson name in the global namespace. Like why don't we just point to it? Like why did we have to copy it into the structure? Right. So now we have this living in two places. Right. So I think on your midterm you should definitely do this. Just use the string copy. Right. You're satisfying the conditions, and it's the fastest way to do it. Can I also do it like this? Oops. This should also work, no? Yeah. But that also puts something into the global namespace, but it's definitely the fastest. Right? Otherwise, if I really wanted to solve this problem to the strictest level, I would have to do something like playa.name at 0 is j, right? Okay, and this is not going to be fun, right? Because remember, this isn't a string literal. This is a character. This is stored as an ASCII value, right? So I could really go through like this, and and whatever, all the way to like whatever this ends up being. I don't know, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh my God, I genuinely guessed. Right? No, I'm just that good. Oh, I'm so good I scare myself. But you see what I'm doing, right? I could definitely go through and like put in the array the individual characters, and everything was done on the stack. Right? So strictly speaking, that last one is the most correct answer. Right? Because we've really restricted all of the memory to stack memory. Okay, but that being said, I hate doing this, so we're going to do this. All right, so we put a string literal in global memory space. There are worse things. Although keep in mind, if you do this too often, you can really fill up your global memory space. What's next? Position. Position is in the stack. Oh, because why do we do the same thing? Because the position is expecting a pointer, right? The name is expecting to live actually in the structure, right? So this structure player has allocated some space in storage. The first 32 bytes is allocated for the name. So you actually have to go put the name into that particular part of memory. Position, as I was saying before, is just the pointer. So it doesn't really matter where I define position. But for this question, they asked us to keep everything on the stack. So this is a way that I can define something that looks like a string literal but isn't a string literal on the stack. Right? So remember, I would have to do something like this, right? But we can do this. There's a shortcut, right? But this is still technically telling the stack how much memory to allocate for third baseman. Okay. Using the same program from the previous slide, allocate space for a player on the heap and point to it with P2. Those are probably better names. Okay, so I'll call this, take playa. Let's just replace this with P naught. All right. Great. Okay. So let's do this now for P2. Let's get rid of this. Okay, so this was initialized on the stack for main. Now let's initialize initialize on the heap. Okay. Where do I start? Well, how do I get these? How do I first allocate space for a player structure on the heap? Yeah, exactly. So I need a struct player pointer p1, and this should point to some space which is the size of the struct player. For now, just let me kill these. Perfect, that works. Okay, so now we have the memory allocated in the heap. Everything else has to go to the heap as well. So now we have a pointer. Right. So now we have to start using this arrow stuff. But I'm going to show you that we don't need to. Right? So suppose I want to fill P1 with 0 home runs. How do I do that? Well, I can't say P1.homeruns is equal to 0. Right? This doesn't make any sense. What have I said? I have P1, which is holding an address, and now I'm trying to get one of those addresses attributes. Doesn't make any sense. What I need to do actually is dereference this. I dereference the structure and get me this attribute. Right? This should work. Right? Let me try printing some of these. So which one do I need? Home runs. Home runs for P1, but I need to dereference P1 before printing it. 0, right? Maybe I'll put this to 2. 2. Okay, so you see, you don't need this arrow stuff. Right? If this arrow confuses you, you can stick with the referencing if you want. But the trouble is that let's try to now to set, well, in any case, this is kind of sloppy, right? Because you have to dereference and then put brackets around it. And if you have recursive structures, this notation gets really messy. So there's like one thing you do in computer science. If you find yourself doing something enough, it may merit extra notation just to simplify things, right? And this was one of those cases, right? So this is equivalent to this statement. That's the same thing. Right, so I should be able to do this. Whoops. Should be able to do this or this. I lied. Oh, home ruins. Jeez. There we go. Okay? So if this confuses you, just remember that it's notation. It's not something extra. It's helping you write something more compactly. And so you can always use the other version. Okay, so what was this question actually asking us for? Okay, so we need to allocate a whole player, and we have to make sure that goes to the heap. Okay, so I can do P1. I can set the home runs. I can set the batting average. What's an average that makes sense? Anyone? 2.7? The other guy was 0.29. Oh, 0.27. No, I'm gonna make him the worst batter. All right. Hey, batter. Okay. Those two things are definitely in the stack. How do I now get a name into the stack? Sorry, stack. These are both in the heap. How do I now get a name into the heap? I can manually do it, but I'm going to do the lazy way. I'm going to use string copy. Right? String copy into name. I don't know, Mr. Baseball. All right, that's a great name. So will this work? And let's take this off. And why don't we just call it the other way, right? This way, just to show you. Oh, I did name wrong. Thank you. Mr. Baseball. Actually, no. Higher stature than that. Professor Baseball. Professor Baseball, Professor Hook. Okay, so I've moved stuff into the heap memory even though we went into the heap memory by way of the global memory space. So this is kind of like, this is lazy, right? And dangerous. Right? Okay, so the one thing remains. How do I now get the position into the heap? Yes? Depends what you mean by better, right?
The safer
It's hard for me to answer this question, right? Because the definitive statement I can say is that it uses less memory to do it in that way. It may not be better because if you forget to put your null terminating character, you've just overbuffered. Well, if string like the way that I'm using string copy here is safer than me doing it like that and not putting in the end. So like that's a really like it. The answer to that question is it depends. Like the only definitive statement I can make is it definitely uses less memory, right? Whether it's better or not is up to interpretation. It depends like by what you're measuring better by, right? So, but you can do something like this on your exam or in your midterms, but you should probably use the string end copy, not the string copy. I don't know. Well, I don't know how we're going to advise the markers. Okay, so we still have to get the, what's it called? Position into the heap. So how do I do that? How do I get, forget about structures. How do I get a string on the heap? Yeah, the answer to getting something on the heap is always use malloc. Malloc is the tool that you have for allocating space on the heap. So I want a character array for another position, 1. And this position, oh, sorry. Position 1. And I need to say that this is malloc. Let's just use the max name size. Or I don't know. What's the position? Anyone? Pitcher. Like this? Okay, I thought maybe that's for like. Okay, so pitcher requires 1, 2, 3, 4, 5, 6, 7, 8. So we need 8 times size of char. So that is now in the heap. And now we need to move. Oh, no, now we just have to. Wait, we haven't declared anything yet. Okay, I have the memory. Now I can tell P1 that like that its position 1 is in this place in memory, but we haven't actually filled position 1 yet. So how do I get something into position 1, into the heap?
Wait, don't you have to say P1 position is equal to position 1?
Oh, yes, sorry. There we go. Yes, you're correct. That makes more sense, yes? Yes, okay. Okay, how do I get now, like I want to put pitcher in there. How do I get pitcher in there? Yeah.
1, 0, 2 options.
Yeah. I'm lazy. String copy into, you know, if I was a good professor, I'd be showing you the better ways of doing these things, but
None of us here have ever accused you of that.
not yet. P1, wait, what was I doing? Oh yeah, into position, I want to copy pitcher. String literal, so I don't have to include it. So there should be enough space there. Let's just give this a print. And I'll do it the other way. Just to mix it up a bit. That's not, I don't want this. Right, and then float for b1.average. That's not going to work. This is going to work. Professor Baseball is a pitcher. He has 2 home runs and an average of .02. Savvy? All right. So what's next? Write a function out of the park that increments the home run counter for a player. For the a player. Who writes these worksheets? It's me. I'm going to have to fix those. Okay, so take care to use the correct prototype. Okay, so we basically want to implement a function out of the park. I hate typing underscores, so here you have it. This out of the park. Okay, yeah, how do I... So there's 2 ways I can do this. So you tell me what the prototype is. Okay, so like what we want to be able to do is pass a player to this out of the park function, and this out of the park function increments home runs. Yeah. Well, you have to use a pointer. Yeah, like this has to be a struct player playa. It has to, right? Because we have to pass by reference. Yes. Pardon me?
Spells it stuck.
Yeah, stuck in the middle with me. Okay, and what should the return type of this be? No. Void, it doesn't do anything. Well, it does something, but it doesn't return anything, right? It's a procedure. Okay, so what's the instruction now to increment the home runs by 1? There you go. That should do it. Yeah? Okay, so let's see. Will this work for both? I'm just going to get rid of this. I don't really want to see those anymore. That's all still initialized. That's initialization. This is initialization. Okay, so what I want to do now is I have 2 players, P1 and P2. So I just want to do 2 printfs. What do I want to print? Home runs. So that's a D. And I want to print P0 to home. Oh, yeah, wrong ones. P0 home runs. P0 home. Oh, no, I want to make sure that, like, I'm going to print it before and then after we run it through the thing. So I'm going to put it, we'll do it one by one. So I'll do P here. Oh, no, that's not going to work. Oh, maybe it will. Okay. So I'll just put P there. And I'm going to say, no, I'm not going to do that. Back to P0. Out of the park. And what do I put here? What are we passing? So I got to pass the address of P0, right? Because I want to pass a pointer to P0. And it's been declared on the stack. Right? It's been declared not as a pointer, but as properly as a structure. And like the difference between declaring an integer or a pointer to an integer. Okay, so will this work? We're expecting to get what? 41, 42? 41, 42. Great. The other one now. Okay, so the other one is P1. So how do I do it? Yeah, so that's how I kind of wanted to do it like this, right? Because I could say something like struct student. I'm just going to define all of these misspellings to my C, and then it will be fine. Struct student, struct player, P. All right, I'm going to say P is equal to P1. And this should work, right? Dereference. Oh, P0. Okay, great, because P0 is like really a thing, right? So here's an interesting question. What happened? So do I have 2 of these player P0s or 1 of them? So you're telling me if I change P0 that it changes P, and if I change P that it changes P0? Then they're different. So settle on an answer. I actually don't know the answer. Right? I just thought of that now. My guess would be that it has to create a duplicate. Right? So, but we can easily check that, right? So we send P through. And then I have to print P0. Yeah. Okay, hold on. So I want to, okay, I made this. Okay, so this will change. But now I just want to see what has happened to P0. Aha. Okay, good to know, right? This will create a duplicate, right? Actually, everything else doesn't make sense, right? Why? Otherwise, you just have a pointer to it, and we didn't declare a pointer, right? So when you do something like this, it will indeed, now we have double P0 in the stack. Okay, so what I wanted to do here, although that was interesting to learn, what do I have to set P2 in order for this all to work for P1? Okay, but note, this has done the same thing, right? Right. So we've dereferenced P1, and now this stack has just pulled in all of that information to the local stack frame, right? By doing it this way. So to do it without making all of those copies, P1. Yep, I will. P1 dereferenced, right? Or if we want equivalently this, and what do I give it now? Just P1, because P1 is a pointer. It works. Great. Oh, should this guy like... I don't know baseball, right? I'm not. You're gonna have to talk with Professor Baseball, right? Check his office hours. Okay. We did 3. We did 4. 5. Okay. So now they want us to do another thing. They want us to declare void foo. They want us to just take a structure player. Same thing. I'm just going to do the same thing, right? And I'm going to say this instead. Okay? What's the difference between this function and this function? In a nutshell, right? Yes, that's the perfect answer, right? I don't want to go through a long explanation of what's happening here, right? Everything can be passed by reference or be passed by value. It shouldn't be surprising that we can do the same thing with structures, right? So this second one here is passed by value. So I just want to show you that if I were to call foo rather than out of the park, that it's like everything gets copied, right? So that nothing is changing outside. So now we have to think of this again because, whoops, I want to, in the middle of here, run foo and check. So let's see. Let's do p0 first. p0.homeruns, p0.homeruns. And what do I send to foo this time? p0 itself, not a pointer to it. 41. We can put a print statement in foo, no problem. Print in foo. Playa.home runs. Runs, runes. Semicolons. God. You guys are so demanding. Oh, print F, come on. All right, so what has happened here is from main, we've passed the structure that's sitting on the local stack frame for main. It gets copied into the local stack frame for foo. It does its thing, it increments it, but then that just gets cleared when the stack frame, when the function returns. Right? So nothing has happened. Like copies have legitimately been made. Let's do the same thing with the other pointer now. So now I want to pass p1, which has been declared as a pointer. How do I get that now how do I pass that by value now? Yeah, we have to dereference it, right? So p1 dereferenced. Oh, why was I passing home runs? Oh, I'm printing home runs. Sorry. Okay, so I still want to look at the home runs. P1 is pointer. And now I want to pass to foo the dereference of P1, right? So this is basically just going to pass it like the values along. Same thing happens. Right? So even though the second one is declared in the heap, you could still pass something in the heap by value. But the thing in the heap doesn't change, right? So passing something from the heap by value means that you're saying, hey, foo, copy this stuff from this part of the heap into your local stack frame, do your stuff, and then when you finish, deallocate that memory, right? It would have been better to pass it a pointer because it's in memory on the heap anyways. But anyways, this is just an elaborate example showing you that you can indeed pass structures both by reference and by value. And be careful. I hope you're getting a little bit more comfortable with this referencing and dereferencing now. What time do we got? No. I was hoping it was an hour later than it was. I'm cranky. I need a coffee soon. Okay, we'll finish this and I'll get my coffee. But I want to explain to you what the next worksheet is because I don't know how to do it. So maybe we can all try to do it together because I'm stumped. Can F affect the local P1 of main? What? Oh, F is what? Okay, so I called it foo. Foo is F. F is foo. Thus concludes your monoworld training. Can F affect the local P1 of main? No. Right? F can only affect the variables that were passed to it, which are getting copied. Right? So nothing, if you have a function which is passed by value, it can't do anything in main. It needs pointers in order to work outside of its memory space. So in other words, after foo of P1 exits, can any data associated with P have changed? No. Repeat the previous two questions. Substitute. I've already done that, so joke's on you. Okay, so that concludes the structure part of the lecture. So I'm going to talk a little bit about the next part of the lecture. Maybe you guys can start working and help me figure this out. Anyway, so this is what you should have learned when you did PCRS, right? You should have learned more in detail about the standard in and standard out. You should know that printf and scanf aren't printing to the screen and pulling from the keyboard. Right? That's what their default behavior is. Printf pushes stuff to the standard output pipe. Scanf reads stuff from the standard input pipe. Right? So there's a big difference there. Remember, we're abstracting input and output. Also know that you have standard in, standard out, and standard error, which is what we're going to talk about next week when we finally do some error handling. Streams can be hooked up into these input pipes, right? So the input pipe may be a file pointer. We have f open and f close. It shouldn't be a surprise that you can manipulate files with C. We have this fprintf, fscanf, and fgets, which we're going to use fread and fwrite. What's the difference between fgets and fread? Pardon me? Well, there's fgets and fread. They either do the same thing or they don't. And if they don't do the same thing, I want to know what the difference is. When do you plan on preparing for your midterm next week? I'm curious. Right? Okay, we have to study a bit, right? I want to be able to pass all of you. And plus, it's much easier to mark exams with answers than without. Okay. The difference between fgets and I want to get it right, so this is embarrassing, but I'm definitely going to Google it, which you could have done. I just always get it backwards or forwards, but the point is I don't know if it's backwards or forwards. Yeah, fgets will read until the first new line. So fgets reads to the end of a line. That could be called fread line. I think we have readline in different languages. Python has a readline, right? Okay, so you can treat fgets like readline that finds the new line. Whereas fread is just going to start somewhere and read a number of bytes or hits the end of the file. Right, so one will read to a new line, that's gets, and the other one reads a specified amount of width from the memory. So if I put that one on the midterm, question 1, we haven't written it, so when I say stuff like this, I could legitimately go next week and put question 1 is what is the difference between fwrites and fgets. All right. Fseek and rewind. Well, this is ways that you can move the file pointer up and down in your file. What about flush? Who knows what flush is? Right, okay, so let's talk a little bit about printf and how much I hate I.O. I.O. is the slowest operation that you can ask your computer to do. That being said, C doesn't print when it hits a print statement. Right? C will run for a bit. It will collect a bunch of prints, maybe like 10 of them, and then every 10 prints, then it will print out everything. Right? Because this is a little bit more efficient than printing every time you hit a print. So some print buffer fills up, and then once in a while, C will flush the buffer, right? As in to, flush, expel, text, print it to the screen. You can actually say in your code, flush. I insist that you now print everything in the print buffer. So the reason we tell you not to use printf for debugging is because something may happen in between your printf and it actually getting printed to the screen. So you could print something, throw an error, and nothing is printed, right? Because now C has stopped executing because it has a critical error or something like that. So technically, you were expecting a print. Like suppose you're trying to isolate where in your file the error is, right? You may never know, right? Because the print never got flushed. So to mitigate against this, you just write your printf and then insist on a flush immediately, right? So then it will print whatever's there. This could be very useful when you're doing. It's like I know I say never use printfs, but when I was coding back in I was told to do multi-threaded and multi-processor and nodal computing, and we didn't have any way of debugging along 1,000 computers. So my only recourse was to use printf. So I hesitate to tell you not to use printf to debug because that's basically your only tool when you're talking about multi-processing. Right? You always have to say something like print the node name and what function you're in, right, and flush. Right? So you can use printf. Just make sure to use this flush or be at least aware that your prints don't print at that line. Your prints will only print once every buffer flush cycle. Okay, so when you define a literal, which goes into the global namespace, did you know that, well, where are those literals stored when I say global namespace? Anyone have any ideas? Right, so when we compile C code into an executable, this executable contains, I don't know, hex values basically, which can be interpreted as machine instructions for the computer. But look at this. Your string literals are literally in your object file. Right? They're there. I can point to them. Right? So your object file will grow depending on how many literals you put it in. So Dan Zingaro has a nice example. I'm going to try to track it down, where he defines some stupidly huge string on the stack, and you have a tiny object file, and then a stupidly large string as a literal, and you have a stupidly huge object file. So I want to be very clear about this. The string literals are literally in the object file. You can inspect them. Okay. So today's yes.
So is this sort of thing what happens with something like a security leak in a program? That it just where they find.
Yeah, I'm happy that you're finally thinking like a hacker. Yeah, maybe. Maybe you look through object code, right? People try to backwards engineer software, right? Because you're given the object code, and you can try to reverse it to try to get the listings back. But yeah, no, go hack. Like maybe my PIN number is in here or something. But now you know, maybe don't store your password as a string literal in your function, right? Like, Jesus, yeah, no, that would be a bad idea. So you could, now you can understand how a human error could cause, could set up a human error can make it so that you can hack a whole system. Oh, I made this a string literal instead of putting it on the stack. Something like that could really screw you. Right, so this is why we're really trying to teach you this stuff. Yeah.
I actually tested that out when I was doing some A1 stuff.
Yeah.
That's why I asked the question which one is safer, because I knew that happens.
Oh yeah, but I don't think Professor Baseball cares too much. He doesn't care too much about his privacy. This John Donaldson though, he's a real jerk. Okay. So the worksheet for the second half of this course, which sorry, go ahead. Okay, anyone have any answers? Where would be the safest place to put a password? On the stack, right? Because we use it and then it disappears, right? Even though technically it's still in memory, right? If you really wanted to be very careful, you should go to that place in memory and just run over with random numbers a bunch of times, right? Or maybe get a drill and drill through your hard drive, right? Okay, so we can look at object files. Right? This kind of looks like this is mostly empty because the symbols in here don't actually, they're machine instructions, which don't have a corresponding, they don't look like anything. They have no character, but they're there, right? The space is a character that doesn't display anything, right? I could write A, and we know A looks like this, but this is a human convention. We didn't bother coming up with symbols to look at the machine instructions. So these things, that's why they're all question marks, basically. I don't know how to render this symbol a bunch of times. So, if you're not running Ubuntu, can't do any of the worksheet today, which was the first problem because I'm not running Ubuntu. Okay, so you're going to have to find a buddy who's legitimately running Ubuntu. I'm now going to log into the Deerfield Hall computers. All right. I'm going to try typing in the correct password. Okay, so I think in here, I have some type of hello world. Oh, yes, I have hello.c here. Okay? This is the most basic hello world program. Well, maybe I didn't have to throw in those headers. But in any case, this is just a program that prints hello world. Let's compile it into hello. Is it me you're looking for? All right. Okay, so we have a output file, hello. Let's just check that it does something. Oops. Hello world. Great. Okay. I said that we can look at the object file that's been created. I mean, this is what it looks like. Let's just check that it does something. Oops. Hello world. Great. Okay. I said that we can look at the object file that's been created. I mean, this is what it looks like. Let's just check that it does something. Oops. Hello world. Great. Okay. I said that we can look at the object file that's been created. I mean, this is what it looks like. Can we track down our literals? Yeah, there's one of them. Oh no, that's the name of the thing. There's the hello world. String literal in the object file. Okay. So the instructions on the worksheet are this. So we can use this tool called object dump. And I want to see everything printed as a string, and I want to jump to the row data. Okay. We can object dump this, and it's going to show us all the information about the object file as strings. Okay? This is a bunch of... So like on the left is the ASCII hex, and on the right is the string. Right? So I don't care about most of this. What I care about is where your string literals are being held is this row data, .row data. Okay, so I'm just going to go back here. I'm going to say just jump to the row data information. So this is really the information that I'm concerned about. So here's baseman. Remember that one day we were doing an example where I was showing you that we could take an integer, like write it out as a binary number, like divide it, and interpret each of the divisions as a character in of themselves. And the conclusion of that was, with one integer, I can store Paul. Right? I can encode 4 characters in one integer. And that's what's happening here. So if I get ASCII to hex converter, and I'm just going to grab, I don't know, this guy. Right? Assman. Proctologist. Right, so if I take this one, this should be RD. And the B. And the space. Right? 4 things. Every ASCII, every hex was representing 4 characters. Right? Because a hex number is 4 bytes, or 1 integer, and we only need 1 byte for a character. So, again, row data, right? This stuff are just the ASCIIs, and then this is the string. Right? This is what you would find if we went into that hex to ASCII converter and did it for each of these integers. Now, here's the problem. Supposedly, this is the address in the object file where the row data starts. It's not. Okay. So, it turns out there's this other piece of information. So it's saying the size of the row data for hello. Oh, I did foo. Oh, sorry, I've been doing foo the whole time. It doesn't. The same thing applies to both. Just let me do this, right? Because like now here's our hello world. But this is giving us different information. This -h. It's telling us that the size of the row data is 10 bytes. The virtual memory address begins here. The logical memory address begins here, and the file offset begins here. Now, it turns out some of the time that the file offset is the thing that's giving you the position of the row data. Now, I tried all day to do this. Like I even have the solutions from last year, and those solutions don't work, right? So this gives you an impression of how fast the technology here moves, right? Material that we had running last year is already out of date because of compiler updates, right? So keep in mind that the ground may be moving. So log into Deerfield Hall Computers, write a hello world program, play around with this object dump, and then what I want you to do is write a program. So what I want to, so like if, like we have the object file, I know that I can walk to a memory address in that object file to find the string literals. And supposedly the information that you require are these ones, right? So I should be able to file seek to this address and print off 10 bytes to find hello world. And that was your task today. So give it a try. It works for exactly one program. Because Firkin did this yesterday and he had no problem. Like, because we were up till like 1 in the morning last night trying to work this out. And it turns out for hello world and only for hello world, everything worked out. So he got very lucky by doing a hello world program. Like I wanted to do this on the struct program because we had a bunch of literals in there already. So give it a try. I couldn't do it. And if anyone can do it, I'll be glad to know how they did do it. So, okay, go be active in your learning while I get a cup of coffee. I'm going to sort of pause the... no, I'll leave it running because I think it's easier to just cut it out when I throw it up. Oh, 808. This is also wrong. This should be integer. I'll be back.
You're good. Machines never work when I hit
Dash S.